Hi and welcome to this Leaving Cert Higher Level Maths revision video. We're going to work through Worksheet 4, which is based on integration. Question 1, we're going to have a bit of integration and the factor theorem. This is a 25 mark question. So part A, find the integral of 4x cubed minus 6x plus 10 with respect to x, so dx. So now what we want to do is to use our rules in our log tables. Just be really careful. In the log tables it tells us that the constants of integration are omitted. That is, when we're doing an indefinite integral like this, it's important that we add the plus c to the end. So the rule is that we add 1 to the power and then divide by that new power. This is what we get. So 4x to the power of 4 divided by 4 minus 6x squared divided by 2 plus 10x. This is following the rule. Then we have to make sure that we add the constant of integration plus c. Tidying that up, we get y equals x to the power of 4 minus 3x squared plus 10x plus c. And that's our final answer. We can't do any more with it. Part B. Part of the graph of a cubic function f of x is shown below. The graph is not to scale, and the graph cuts the x-axis at 3 points, a, b, and c, and we know a, which is 2, 0. Given that f dash of x, so the first derivative of 6x squared minus 54x plus 109, show that f of x, the actual function, is given here. So we want to show, knowing that we have the first derivative, we want to work backwards. So remember, integration is the backward step of differentiation. So really what we're being asked to do is to integrate f dash of x. We need our rules of integration, and we'll set it up like this. So our function will be the integral of 6x squared minus 54x plus 109 dx. Working with our rules, add 1 to the power, divide by the power. And again, remember, in our log tables, that rule, the constant of integration is omitted, so you need to make sure you have a plus c there at the end. Tidying it up, we get f of x equals 2x cubed minus 27x squared plus 109x plus that constant. Now, they specifically wanted us to get f of x, this specific function. The function that we found has a plus c, so there's an infinite number of values that c could have. So technically there is so many different functions that this could be, but we want one specific one. So we need to have an extra piece of information. And we do. The fact that they gave us a point that's on the function will allow us to find an actual value for c rather than leaving it as just a plus c there at the end. So we're going to use that point to 0, 2 being the x value, 0 being the y value. Remember, f of x is another way to say y. We're going to sub it in. So here is what I have so far with my plus c. I know that the 0.20 is an element of that. Subbing it in, f of x, another way to say y, so the y coordinate 0, the x coordinate is 2. Subbing that in, tidying it up, we end up with 0 equals 126 plus c, so c equals negative 126, which is what we expect because they gave us what we wanted. So this is our final function as they asked, so we add in a little QED. So part B, part 2, find the coordinates of B and C. So this is actually asking us about factor theorem. We're using this idea of trial and error, finding a root, then we know a factor and divide a factor in. Now, there's no need for trial and error in this particular case because we already know one of the roots. We have A, we have B, and we have C, but we know A. So without the trial and error, I can say straight away that x equals 2 is a root. I've taken that from my graph, which means that x minus 2 is a factor. The fact that it's a factor means it will divide in evenly, i.e. with no remainder. So let's do some long division. So we're dividing x minus 2, the factor, into the cubic that we worked out in part I. Now when we worked it out, they did tell us what the answer should be, so that allows us to know for sure that we're working with the right function and it won't upset this particular part. So dividing in, remember we always divide the first term into the first term. So in this case, 2x cubed divided by x, that gives us 2x squared. You can place that in either place. When I write it, I tend to write it in the first one, but we can do a little column here for x squareds. Then we multiply. So when you multiply 2x squared by both x and minus 2. Then we change the signs. Okay, that's subtraction, so taking them away, but taking them away effectively makes a change of sign. And then we have minus 23x squared, bring down the next piece, and we start again. So divide first term into first term. That gives us minus 23x. We multiply, we change our signs, we then tidy it up and we get 63x. We bring down the next part and we try again. So again, divide, so we get plus 63, multiply, change our signs, and we're left here with no remainder. So now we have a second factor of this cubic. Now it is a quadratic, but that means we can break it down further. So I'm going to use guide number. You don't have to. If you find that these numbers are very, very big, you can go straight to minus b. That's perfect. There's no indication here telling us to do it to so many decimal places or telling us to do it in third form. So I know there's probably no need for me to use the minus b. Factorization should work. So I break that down, bit of trial and error. I get minus 17 by minus 18. And I work it through, and by working it through I end up with x equals 7 over 2, or if you prefer 3.5, or x equals 9. They are the two roots. So b is written here as 7 over 2 or 3.5, and c is 9, 0. Question 2, integration for calculating area and also an inverse function. So now let's use integration for area. This is one of the main reasons why we use integration. It's to find the area between two curves or an area underneath a curve. Part of the graph of the function h of x equals x and k of x equals x cubed are shown in the diagram below. Find the coordinates of the point of intersection of the two graphs. So we're trying to find where is h of x equal to k of x. So we have x equals x cubed. So what we're going to do, we're going to bring the x across, equals 0, and we're going to use some factorization. X squared minus 1 equals 0. So we did highest common factor, but we can also do difference of two squares. X plus 1 equals 0. That's now fully factorized. So we get x equals 0 is 1 point. X equals 1 and x equals minus 1. So there's our 0, there's our 1, there's our minus 1. So that looks about right. So there's a bit of symmetry going on. There's 5 boxes to the right, 5 boxes to the left. There are just our x values. We then need to figure out, well, what would be the corresponding y values. So I'm going to do h because it's easier. So that's 0. H of 1 is 1. H of minus 1 is minus 1. So our points are 0, 0, 1, 1, and minus 1, minus 1. So we also know that that is 1 and that is minus 1. So there are points of intersection. It then asks us, find the total area enclosed between the graphs of the two functions. So what we're trying to find, just to highlight it, is this area in here. So that piece there and this piece here. Now what we have is a symmetrical function, so both of those two areas will be the same. So if we could figure out one of those areas, then we'll be able to double it. So I'm going to focus on the top part. So I'm going to find the area under this curve and the area under this curve. So that's this piece in red. And when I take them away, I will get the bit in between. So you want the area under h of x. So what we want is we're going to integrate h of x between 0 and 1. And then we're going to take away integrating between 0 and 1 as well, k of x. Now, I'm going to put that in terms of the actual x's. So between 0 and 1 we have x minus, so I forgot my dx, cannot integrate without dx, minus 10 x cubed dx. So what would actually be easier is to combine these into x minus x cubed dx. And if we can integrate that, we'll be able to get the area of one piece. So what I'm going to do then is I'm going to basically multiply this by 2 to get the full area. We're going to do this differentiation or this integration now. So it's 2. When you integrate, we're going to have add 1 to the power, divide by the power, add 1 to the power, divide by the power, and that's going to be between 0 and 1. So we get 2. And here we have 1 squared over 2 minus 1 to the power of 4 over 4 minus 0 squared over 2 minus 0 to the power of 4 over 4. And when you work that out, we end up with a quarter minus 0, which is basically 2 times a quarter, which is a half square units. The last part of this question asks us on the diagram, using symmetry otherwise, draw the graph of k inverse and the inverse function of k. Now, so if you want to think about that inverse of a function geometrically, effectively what it is, it's the image of the function under axial symmetry in the line x equals y. And luckily we have the line x equals y here, and we're going to use that as basically the axis of symmetry. So what we end up with is this line here. So see that it's the mirror image of k of x through the line x equals y. So we were very lucky they gave us that. So I'm just going to label this. So this is k inverse of x. So if they didn't give that to you, you could draw that and basically graph k inverse. Another way you could do it is you could work out what k inverse is, which we have seen how to do in chapter 2, and you could then get some points. That's much longer, and this is also just really a sketch. They're not looking for anything terribly accurate. They want to see the curve, they want to see that symmetry, but they're not going to penalize you for not having exact points, especially given that they said using symmetry or otherwise. Question 3. Integrating trigonometric functions and calculating average value. This is a 25-mark question. Part A. Find the integral of 5 cos 3x dx, so with respect to x. So when we integrate a trigonometric function, we need to remember that integration is the backward step of differentiation. And why I say that is because when we are differentiating our trigonometric functions, if it was anything more than cos x, sin x, tan x, so there's anything more than an x there, we had to use a chain rule. So the chain rule was that to fix that differentiation, we had to multiply by the derivative of the inner function. So what needs to happen here is we have in our log tables, page 26, the rules of integration for trigonometric functions. They're down here at the end, cos, sine, and tan. But since this is a cos 3x, so it's not just a cos of x, we need to make sure that we divide, because we're integrating, by the derivative of the inner function. So the derivative of 3x, so it means we're going to divide by 3. So this turns into 5 over 3 sine of 3x. But again, remember, this is an indefinite integral, which means it doesn't have limits of integration. It means that this needs a constant. The constant of integration is omitted in the log table, so make sure you add your plus c there in the end, and that's it. Okay, so just be careful. It's It's very easy when you know how, but you need to remember when we're looking at trigonometric functions how there was a piece of the chain rule, and now that we're integrating, we need to keep that but work backwards. Part B. The slope of a tangent to the curve at each point x and y is 2x minus 2. So they've told us that the slope is 2x minus 2. Another way to say slope is dy dx, or because we're working with functions, f of x, we can talk in terms of f dash of x. So this thing that we've just been given, this is f dash of x, the slope of the tangent to the curve. So now they told us that the curve cuts the axis at minus 2, 0. So that's a point that's on the actual curve. It's actually one of its roots. And we want to work and get f of x. Now, if we know the first derivative, f dash of x, the slope, we can work backwards to get f of x. That backwards step, that is integration. So we're integrating that slope, 2x minus 2, with respect to x, so dx. We work backwards, add 1 to the power, divide by the new power, we get y is actually equal to x squared minus 2x. You can also use f of x here. I've just used y to make it easier for the next few steps. When we work with the indefinite integral like this, it's really, really important to remember that the rules in the log tables only give us the basic rules and the constant of integration is omitted. So here we need to make sure that we add in our plus c. Now, because they wanted an actual function, this is technically not a function because we don't know what c is. If they wanted us to leave it in terms of c, they would have been very clear about that. We were given another piece of information, and that was that point minus 2, 0. So we can use that, and knowing that it is a point on this function, we can figure out what c is. So I'm going to sub it in. X is minus 2, y is 0. This works out as c is minus 8. So our final answer for f of x is x squared minus 2x minus 8. Part 2. Find the average value of f over the interval 0 is less than or equal to x is less than or equal to 3, where x is an element of the real numbers. So we have a formula for that, and the formula is here. Now this formula is not in the log tables. You need to know it off by heart. I would suggest that you do a little bit of work on where it comes from to really truly understand this. The more you understand it, the easier it'll be to remember. So I'm going to take my function f, which I've written here as x squared minus 2x minus 8, and we are going to integrate that between a and b, so between 0 and 3, and we're also going to sub in 1 over b minus a. So it looks like this, 1 over b minus a, 3 over 0, integrating the function itself between 0 and 3 with respect to x. So when I work this through, I have a third. Integrating, add 1 to the power, divide by my power, I get x cubed over 3 minus 2x squared over 2, which simplifies to just minus x squared, and minus 8x. I'm looking to evaluate that between 3 and 0, so I'm going to sub in x is 3 and x is 0 and take them away. When I do that, final answer works out as minus 8, and this is the average value of f over that interval. Question 4. Calculating area using integration and the trapezoidal rule. This is a 25-mark question.
So example 4.7, the trapezoidal rule. So there is a strong link between the trapezoidal rule and integration. So trapezoidal rule is a way to estimate area, while integration is a more accurate way to calculate area. And often we see trapezoidal rule and integration linked because if you do it one way and do it the other way, you're getting two similar answers, but one is accurate, one is an estimation. We'll see in this question how that works. So the diagram shows the graph of the function y equals sine of x. So we're in trigonometry as well. In the domain 0 is less than or equal to x is less than or equal to pi. So at this point you should have a word jumping out at you, and that word is radians. So if you're going to use your calculator, you need to make sure it is in radian mode now. They want us to complete the table, and they want it correct to 3 decimal places. 3 decimal places. So putting them into the calculator, we get 0, 0.5, 0.866, 1, 0.866. We have a bit of symmetry going on, which makes sense when you see the diagram, and 0. It then asks us to use the trapezoidal rule. So here's our trapezoidal rule from our log tables, and that is the area is approximately equal to h. Now what h is, I have in the diagram there from our log tables, but h is basically these distances here. So that's h. They're all h. Now the easiest one to kind of spot the h is the first one, because it goes from 0 to pi over 6. So what we end up with is h is pi over 6 all over 2. And then we have y1, y2, and so on. So I'm just going to label it. This is y1, y2, y3, y4, y5, y6, y7. So we have 7 y's. And we basically take y1 and yn. So the first one plus the second one plus 2 times the rest of them. So basically what happens is it's an average of the first one and the last one, and then we basically take into account all the middle ones. So you had 0.5 plus 0.866 plus 1 plus 0.866 plus 0.5, and that can go straight into your calculator, and we get the area is approximately equal to 1.95407. They didn't tell us about rounding, so I'm going to leave it in around there. The next part of this question asks us to use integration to find the actual area. So for integration, we're going to integrate between 0 and pi the function sine of x. So we're doing dx. And what that gives us, sine integrates to minus cos of x, so nice and straightforward. And we're doing it between pi and 0, which is minus cos of pi minus cos of 0. And what that effectively gives us is minus cos of pi plus cos of 0. Remember, we're still in radians, which is minus 1 plus 1, which gives us 1 plus 1, which is 2. So that is our area. And now they want us to find the percentage error in your answer to part B. So first of all, we calculate the error, and then we put it over the actual. And to make it a percentage, we multiply by 100 or 100 over 1. So the error is going to be 2, which is the actual one, minus what they said, 5407. And we're going to divide that by the actual and multiply it by 100. So that little formula, the error over the actual and then multiply it by 100, is a great little formula for any kind of percentage error. There's an error of about 2.3%. We don't have to worry about being too big or too small, the plus and the minus. The percentage error is just how much of an error, or what percentage of an error is there. It doesn't matter bigger or smaller, so plus or minus, you can take the absolute value.
Question 5. Differentiating trigonometric functions and calculating average value. This is a 25-mark question. So part A, let h of x equal cos of 2x, where x is an element of the real numbers. A tangent is drawn to the graph of h of x at the point where x is equal to pi over 3. Find the angle that the tangent makes with the positive sense of the x-axis. Now, this question, because of maybe how it's written, it seems like quite a complicated question, but let's break it down. It says the tangent is drawn to the graph at the point where x is equal to pi over 3, and we want to find the angle that that tangent makes. Now, the angle, and tan in particular, is very much linked to slope. So really what we're looking at is the slope of the tangent. So we're actually talking about differentiation. So we're going to first of all differentiate h of x. That gives me minus 2 sine of 2x. And now we want to specifically look at it where it is pi over 3. So we are subbing in pi over 3. Now, one thing to be really, really careful of here is that we're working with radian. So if you're going to your calculator, make sure that you have it in radian mode. So in a Casio, there will be an or at the top. In Sharp, you're going to have an or AD. So we're taking our h dash of x, the first derivative, and we're finding h dash of pi over 3, putting that into the calculator, and we end up with minus root 3. Now, what I'm going to do is I'm going to sketch this out. You can do it without a sketch, but I think it's going to be much more challenging. So what we've just worked out is the slope of the tangent to the curve at x equals pi over 3. If we think of what pi over 3, I suppose, if we think of, what minus root 3 actually means, it means we're going to have a negative slope, so it's going down, and the slope is root 3. So I've just drawn a line here, and the slope of that is negative root 3. Now, what we've been asked to do is to find the angle that this tangent makes with the positive sense of the x-axis. So the positive side, the right side. So we're basically looking for this angle here. So we know the slope is minus root 3. We know the tan is minus root 3. So what we actually can do is work backwards and get tan inverse of minus root 3. Now, I wouldn't necessarily tell or encourage you to use calculators here. It's just fine. You'll get that answer. But it's because we're dealing with an obtuse angle. So we're between 0 and 180. So the calculator will give you the correct answer. It won't always. Okay, that works for tan. It doesn't work for sine because we have sine is positive in the first and the second quadrant. So we just have to be very, very careful. So here it will work. We're just going to do tan inverse and we end up with 120 degrees. Part B. Find the average value of h of x over the interval 0 is less than or equal to x is less than or equal to pi over 4, where x is an element of the real numbers. Give your answer in terms of pi. So here we're talking about, again, a trigonometric function. We want to get the average value. So there's my trigonometric function. Here's my average value formula. Again, remember, you need to know this off by heart. It is not in your log tables. So now what we're going to do is we're going to sew into that formula. It's going to look like this. I know it's nasty, it's messy with that pi over 4, but trust it, use your calculator where you need to. 1 over pi over 4 minus 0 will simplify to 4 over pi. And then we're going to integrate cos of 2x dx between 0 and pi over 4. As we saw earlier in the video, it's good to remember that when we integrate trigonometric functions, and they're not just an x, so it's not cos of x here, like cos of 2x, we need to work backwards and think about how we differentiate it, and we differentiate using the chain rule. So we would have always multiplied by the derivative of the inner function. Now, because we're integrating, to integrate this cos of 2x, we integrate it like cos, but then to take account for the fact it was 2x, we divide by the derivative of the inner function. So we end up with something like this. Pi over 4 times cos goes to sine of 2x over 2 because you're dividing by the derivative of the inner function. The inner function is 2x as opposed to it just being an x. We're going to evaluate that between pi over 4 and 0. Be very, very careful. Oftentimes we think, oh, it's 0, so the answer will be 0. Not necessarily. Be very, very careful when you're doing trigonometric functions. The cos of 0, for example, versus the sine of 0. Cos of 0 is 1, sine of 0 is 0, so just always double check. When we work through this and evaluate it, again, another area just to be very careful about. When we work with this, we are working in radians, so make sure your calculator is in radians, and we end up with a final answer of 2 over pi. If your calculator won't give you back it in terms of pi, so sometimes that happens. So when we're working with fractions and pi is in the denominator, so for example, pi over 4 multiplied by a half, you're going to have to do this yourself, or you're going to have to ignore the pi in your calculator, so put it in just 4 by a half, and that's 2, and then put the pi back in under the line. So we've seen this asked in a few different questions where it's not possible just to use your calculator to give your answer in terms of pi. So be very, very clear about how you can work to ensure that that pi stays and you're able to keep that pi in your answer without relying on putting the whole thing into the calculator.